Hello and welcome to a video on graphing rational functions. And this is a video where we're going to start with the easy and progress gradually towards rational functions that have more and more pieces and more involved. But every time we do the same thing. First we make sure that our function's factored, and if it's not, we factor it. We look for holes, if there are any, intercepts, vertical asymptotes, domain, and behavior asymptote, and then we put together a graph. Sometimes you don't know the domain until you're done with, well, you know the domain, but you don't, we can say the domain and range once we're looking at the graph. All right, so the first one, notice that this first example is already factored. There's nothing to factor here. There's nothing to cancel, so there's no holes. So we go right to the x-intercepts. So x-intercepts, remember, come from the numerator. So we're going to look at, for the x-intercepts, we're looking at x plus 2 equals 0, or x equals -2, and that's the only x-intercept. Then we look at the vertical asymptotes, and that comes from the denominator where this thing is undefined. So that's going to be the 0 of the denominator, where x plus 4 equals 0, or x equals -4. Then we look at the y-intercept, and the y-intercept is f of 0. And for f of 0, I usually just look over here. 2 over 4, that's 1/2. So the y-intercept is going to be y equals 1/2. And then last, I'm going to look at the end behavior. And the end behavior, this is a case 2. Both numerator and denominator each have the same degree. They're each first degree. So there's going to be the end behavior is going to be based on just saying y equals that term over itself, x over x, which is 1. So y equals 1. It's a horizontal asymptote at 1. All right, let's put this basic information in here. So first we've got, let's put our asymptotes down first, and there's one at -4, so let's put the vertical asymptote in there. Let's put the horizontal asymptote in here at 1. And that's going to frame the graph. Now let's plot our intercepts. So we have an x-intercept at -2. A y-intercept at +1/2, looks like right about there. And it looks like we've got already a pretty good idea of the path of the branch of this. Now there's a branch on the left side and the right side of that vertical asymptote, and we've got a pretty good idea of that branch on the on the right side already. It's going to approach the asymptote. And on the left side, we have a pretty good idea too, because we know it cannot be down here. It can't be down here because there would be another x-intercept. There's no way it can hug both of these asymptotes without crossing the x-axis. So we've got to have a branch on the left side of the asymptote and on the right side, and it looks like that. Okay, that's it. All right, let's look at another example. Okay, a little bit more involved because this one looks like it could use some factoring as a first step. So let's go ahead and factor. So this numerator factors to give us two terms. X, 3 and 2 gives us 6, and subtracts to give us 1. So 3 and 2, and we'll make this negative and this positive, and that's a nicely factored numerator. What about the denominator? Let's pull out a -4 times x plus 3. Okay, so it looks like we have there's no common factors. And by the way, if you're looking at this like I am, you should be, and saying, what if I took out a +4? Then I would have a -x minus 3. Almost looks like something would cancel, but it's not the same. X minus 3 and -x minus 3 are not the same thing. So we can't get that. I'm still going to be cautious about our vertical asymptote, and here's what I mean by that. Let's get our x-intercepts. That's pretty standard here. There's nothing unusual about that one. So the x-intercepts are going to be where x minus 3 equals 0, or x equals 0. And then there's another one where x plus 2 equals 0, or x equals -2. So there's our x-intercepts. For the vertical asymptote, just to be sure, I'm going to set the whole denominator equal to 0. So I'm going to set, you can think of it as just -4 times x plus 3 equals 0. Now, it doesn't matter how you write this down. You're going to get the same thing. You're going to get a -3 as the only possibility. But if you had also looked at the original denominator, -4x minus 12 equals 0, either way, divide by -4, and you're going to get x plus 3 equals 0, so x equals -3. And there's our vertical asymptote. All right, our y-intercept will be the easiest way to find the y-intercept, again, is looking at it in polynomial form. So the y-intercept would be visually right there, -6 over -12, 1/2. So the y-intercept is y equals 1/2. What about end behavior? Unfortunately, and we always hope that's not the case, but when we have a numerator that's more than the denominator, it just means there's an extra step and we have to do long division. So we have to do, for the oblique asymptote, we have to do -4x minus 12 into x squared minus x minus 6. And we're going to drop the remainder and we'll have our oblique asymptote. So -4 times what equals x squared? It's one of those where it's a fraction, so I'm just going to write it out. So I'm going to write down exactly what I just said. I said -4x times what equals x squared. And that makes it a little bit easier to see, I think. So we divide both sides by -4x, and we get a equals x squared over -4x, which is -1/4 x. That's what goes up here. When we multiply that by -4x, we get x squared. When we multiply that times -12, we get 3x. And we subtract. So we get x squared minus x squared is 0, -x minus 3x is -4x, carry down the -6, and do it again. This time it's going to just be 1, right? 1 times -4x is -4x. 1 times -12 is -12. Subtract this, we get 0, and then -6 minus -12 is 6. That's the remainder. That just goes away. And our oblique asymptote is y equals -1/4 x plus 1. All right, now let's start plotting. We'll plot our asymptotes first. So I'm going to plot my vertical asymptote. It's simple at -3. So here it is. The oblique asymptote that we just found has a y-intercept of 1 and a slope that goes down 1 and over 4. So it's like right there, something like that. And then we can just go to the left 4 and up 1 just so we get another point there. And I think I'm going to, I'm just going to freehand it. Okay, now we still look to the left and the right of our vertical asymptotes. Always the vertical asymptote you look to. That's what divides the branches of the function. So on the left side of that, well, let me plot my x-intercepts first. That's kind of important. I have 1 at 0. I have 1 at -2. And I have a y-intercept at 1/2. Okay, well, I made a mistake, and you probably were thinking, what's he doing with that 3? Why did he say 0? Well, this can't be a y-intercept, and I knew because you can't have 2 y-intercepts in a function. So this is my mistake right here. X minus 3 equals 0 doesn't mean x equals 0, it means x equals 3. So let me plot that one now. 3 is right there. And that's kind of confusing because it's right on the asymptotes. That might give us a little bit of trouble, but it's okay to be on the oblique asymptote. And is it right on the oblique asymptote? Not really, because we know that that asymptote actually goes at 4 here. So it's really right below that asymptote. And then we've got the y-intercept at 1/2, and now it makes sense. And I think, like I said, this is a little bit below the asymptote, and I think what's happening here is it's going to go like this, and then it's going to go like this. Now it may, we're not looking at this yet, and you can if you want, but we're not going to explore whether or not this curve crosses the oblique asymptote. You can set it equal to the oblique asymptote. In other words, you can set the function here. Since there's nothing canceled, you could just set f of x equal to the oblique asymptote here and see if you get any values when you solve it for x. And if you do, that's the x value where the curve crosses the asymptote. We're just going to do that a little bit, if at all, but not this example. Now the other branch on the left side has to be up here because, again, we know that it can't have any more x-intercepts, so no need for a sign chart, and there's the function. Okay, let's look at the next example. Okay, I'm going to go ahead and factor this and break it down and get all of the information, then we'll put together the graph. Okay, we've got our 4 pieces of information. We've got our vertical asymptotes, x-intercepts, y-intercept, and behavior. Let's put those asymptotes down on the graph. So we have 1 at 3, 1 at -3. So there's now 3 intervals that will be defined, 3 branches that we're going to need to look at here. We've got a y-intercept at -1. And we've got x-intercepts at 4 and -4, here and here. And we've got a y-intercept at -16/9. That's something like right here. Okay, now those 3 points are actually enough to put together the whole graph. On the left side of the first vertical asymptote, it's got to go up towards the asymptote and approach the asymptote there. And on the right side, it's kind of the same thing. It's got to go up towards the asymptote and approach that asymptote there. And in the middle part, it can't be one of those cubics. Now, if you're thinking could be the cubic or could be like the U shape, you're right. In this case, it's the U shape. Can't be the cubic because if it were, it would have another x-intercept. So the only thing it can really do, now it might go up first, but we're going really rough graphs here without using a calculator, and that's it. There's the graph. All right, let's try one more. So let's, this one I believe has a hole, so we get some practice with the hole. So let's first factor it and then find all of our pieces. Okay, so this one has a hole. We got the hole. We notice that there's a common factor of x minus 1, so when we reduce that, we get a reduced function right here, but it has a hole where that factor equals 0, which is at 1. So we know the hole's at 1 f of 1. We found f of 1. It's 4/3. Actually, it's 4 over -3. And then we worked with our reduced function for the rest of the problem. We found our x-intercept from this. We found our y-intercept from the denominator. We found our our x-intercept from the numerator, our vertical asymptote from the denominator, our y-intercept. I looked back over here at this, and I got the -3/4, and then I looked at this for my end behavior. Okay, let's plot these pieces. So I've got a vertical asymptote at 4. I've got a horizontal asymptote at 1, y equals 1. So there's only 2 branches to this one. And I'm just going to have to figure out what happens on the left side and the right side. Hopefully I have enough clues here. Let's see what happens. I know I have an x-intercept of -3. So there's an x-intercept right there. I know I have a y-intercept of -3/4 right there. And I know I have a hole at 1 -4/3. So 1 -4/3 is something like that. So I've got the path on the left side of the vertical asymptote. It's going to have to approach the asymptote, connect over here and approach that asymptote. And the other branch has to be on the top, because if it was on the bottom, there would be another x-intercept, and there isn't. Okay, I hope you found this helpful.